Algorithm, the secret to modern life. The analytical engine weaves algebraic patterns, just as a jacquard loom weaves flowers and leaves. Ada Lovelace. Wow. Our lives are run by algorithms. Every time we search for something on the internet, embark on a journey with our GPS, choose a movie recommended by the Netflix or seek a data online, we are being guided by an algorithm. Algorithms are ubiquitous in the digital age, yet few realize that they predate the computer by thousands of years and go to the heart of what mathematics is all about. The birth of mathematics in ancient Greece coincides with the development of one of the very first algorithms. In Euclid's Elements, alongside the proof that there are infinitely many prime numbers, we find a recipe for solving a certain type of problem. Given two whole numbers, it allows anyone who follows its steps to find the largest whole number that divides them both. Okay? It may help to put the problem in more visual terms. Imagine that the floor you need to tile is 36 feet long by 15 feet wide. You want to know the largest size of square tiles that will perfectly cover the floors. So what should you do? Here is the algorithm more than 2,000 years old that solves the problem. Suppose you have two numbers m and n, and suppose n is smaller than m. Start by dividing m by n and call the remainder n1. If n1 is 0, then n is the largest number that divides them both. If n1 is not 0, then divide n by n1 and call the remainder n2. If n2 is 0, then n1 is the largest number that divides m and n. If n2 is not 0, then do the same thing again. Divide n1 by n2 and call the remainder n3. These remainders are getting smaller and smaller and are whole numbers, so at some point one must hit 0. Wow. When it does, the algorithm guarantees that the previous remainder is the largest number that divides both m and n. This number is known as the highest common factor or greatest common divisor. Sure. Now let's return to your challenge of tiling the floor. First, imagine the largest square tile that could fit inside the original shape. Then look for the largest square tile that will fit inside the remaining part, and so on, until you hit a square tile that finally covers the remaining space evenly. This is the largest square tile that will cover the whole space. Sure. Please look at the diagram.
Εκεί ψηλά που φτερουγάς, να πεις του μακρύ η σταύρωση δεν τέλειωσε, μ' Ανάσταση θα έρθει. Η σταύρωση δεν τέλειωσε, μ' Ανάσταση θα έρθει.
How does it feel like to do this?
I don't know. I wonder what I'll be asked in many years' time.
You can't actually train for this. Oh yes.
If m equals 36 and n equals 15, then dividing m by n gives you 2 with a remainder n1 of 6. Dividing n by n1, we get 2 with remainder n2 of 3. But now, dividing n1 by n2, we get 2 with no remainder at all, so we know that 3 is the largest number that can divide both 36 and 15. Wow! You see that there are lots of it. Lots of if blah blah blah, then blah 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 clauses in this process. Clauses, yeah? It's all about grammar, right? Syntax. That is typical of an algorithm and is what makes algorithms so perfect for coding and computers. Euclid's ancient recipe exhibits the 4 key characteristics any algorithm should ideally possesses. If consists of the precisely stated and ambiguous set of instructions. It consists of a precisely stated and ambiguous set of instructions. Its procedure always comes to a finish, regardless of the numbers inserted. It does not enter an infinite loop. Wow, infinite loop. It produces the answer for any values input. It is fast. In the case of Euclid's algorithm, there is no ambiguity at any stage. Because the remainder grows smaller at every step, after a finite number of steps it must hit 0, at which point the algorithm stops and spits out the answer. The bigger the numbers, the longer the algorithm will take, but it's still relatively fast. The number of steps is 5 times the number of digits in the smaller of 2 numbers for those who are curious. Sure. If the invention of the algorithm happened over 2000 years ago, why does it owe its name to a 9th century Persian mathematician? Algorithm is a Latinized form of a surname, that of the Muhammad ibn Musa al-Khwarizmi. Sure, Uzbekistan, right? One of the first directors of the Great House of Wisdom in Baghdad, al-Khwarizmi, was responsible for many of the translations of the ancient Greek mathematical texts into Arabic. Although all the instructions for Euclid's algorithm are there in the elements, the language Euclid used was very clumsy. The ancient Greeks thought about mathematics problems geometrically, so numbers were presented as a line of different lengths and proofs consisted of pictures. Sure. Proofs consisted of pictures. Yes, sure. A bit like our example of tiling the floor. But pictures aren't sufficient for doing mathematics with much rigor. Sure. For that, so the pictures is the main. The sentence is not main, right? For that, you need the language of algebra, which uses letters to stand for variable numbers. This was the invention of al-Khwarizmi. To be able to articulate the working of an algorithm, we need languages that allows us to talk about numbers without specifying what those numbers are. We already saw this at work in Euclid's algorithm when we gave numbers to the numbers we were trying to analyze. N and M, these letters can represent any numbers. The power of this new linguistic take on mathematics was that it allowed mathematicians to understand the grammar underlying how numbers works, rather than being limited to showing a particular example of a method working. This new language of algebra provided a way to explain the general patterns behind the behavior of numbers. Today's easy analogy is to think of the code behind the learning software program. Sure, no matter what numbers are plugged in as inputs, it works to yield an output, the third criterion in our conditions for good algorithm. Indeed, algorithms have gained enormous currency in our era precisely because they were perfect for computers. Whether there is a discipline pattern underlying the way we solve a problem to guide us to a solution, an algorithm can exploit that discovery. It is not required of the computer that it think. It need only execute the steps encoded in the algorithm and again, as if by magic out pop the answers we seek. Sure.